All right, here's chapter 7, problem number 59. It reads, the ropes in figure P7.59 are each wrapped around the cylinder and the two cylinders are fastened together. The smaller cylinder has a diameter of 10 centimeters and the mass of 5 kilograms. The larger cylinder has a diameter of 20 centimeters and a mass of 20 kilograms. What is the angular acceleration of the cylinders? So the first thing I did was I redrew that picture that they referenced with our two masses hanging off of it, and we've got the different diameters, pulleys, and they're fastened together. So this problem's pretty difficult. We need to start first. We know that these two masses, the 2.5 kilogram and the 4 kilogram, both apply a torque to their respective pulleys. But the tension that they apply, right, because they're actually wrapped around ropes, their tension is not equal to their weight. So we need to first find the tension in each rope because of these weights. So it's going to be a combination of Newton's second law and the net torque acting on this so we can solve this problem. So the first thing we should do is for the small mass, let's draw a free body diagram. You'd have mass of the small times gravity times its tension, right? We'll call that T tension of the small. Doing that, we find that then the Newton's second law for this would be F net equals ma, and we would have T sub, let's go back just a quick second. We're in the wrong direction. It's going to cause the pulley to go in the counterclockwise direction, which we say is positive. So it's going to be m small g minus t is equal to m small times a. And if we reference real quick, we know that a is equal to alpha r. We can make that quick change, solving for the tension. So the actual force pulling on this larger pulley is going to be T small is equal to m sub s g minus m sub s times alpha r sub s, making that substitution. If we do the same thing over here for the large mass, right, that 4 kilogram mass, our free body diagram is the same, pretty much that, and then we've got T large going there. F net is equal to ma. But in this case, the tension in this rope is going to be in the counterclockwise direction. So really, the pulley is going to rotate in the opposite direction. So it's going to go against our convention. So this will be then T minus m sub L g is equal to, and I'm going to make this substitution real quick, m sub L alpha r sub L. And finding that tension, we've got then m sub L g plus m sub L alpha r sub L. So there are the two forces that are going to be acting on our system here. And now we can go about and we can find what is the actual angular acceleration for this pulley. So to do that, it's going to take a little bit of work. So we know that torque is equal to I alpha. Now the net torque is going to be this tension of the small, torque from the small one, minus the torque of the large is equal to I times alpha. Okay. Now, if we take all this stuff, this is going to be now the tension here times the radius. So it's going to become a little busy. So we're going to go with R sub s, and then m sub s g minus m sub s alpha r sub s, and then minus r sub l m sub l g plus m sub l alpha r sub l. And then the next thing we need is this moment of inertia term. So this moment of inertia term is the net moment of inertia for the entire thing, and it's made up of two separate pulleys. So these two separate pulleys each have their own moment of inertia, and because it's a solid cylinder, they follow the equation of I equals 1/2 mr squared. And to find the moment of inertia of this entire pulley, it's just the sum of the individuals. So we can write this out to be 1/2 mass of the small, radius of the small squared, plus 1/2 radius of the large, mass of the large times the radius of the large squared, all times alpha. So now we got a lot of stuff here. It's just a matter of plugging all the good stuff in. So when we start doing that, we're going to go with 2.5 times 0.1 times 10 minus 2.5 times 0.1 squared times alpha minus 4.05 times 10 minus 4.05 squared times alpha equals 1/2. Now this mass is the mass of the pulleys and the radii of them. So this will be 1/2 5 times 0.05 squared plus 1/2 20 times 0.1 squared, all times alpha. So if we do all the algebra, we do all the math, we're going to get 2.5 minus 0.025 alpha minus 2 minus 0.01 alpha is equal to 0.10625 times alpha. And if you can do the math, you can do the math on your own, figure it out. We find that alpha is going to be 3.54 radians per second squared. So this problem has, I think, two key points to it that make it a difficult problem. The first is that, remembering that the moment of inertia of this entire pulley is the sum of the individual cylinders, these individual moments, which we did over here. We added the two of them together. And then the other tricky part is remembering that the tension in the ropes, these individual ropes, is not equal to the weight of the two masses here. It is equal to the sum of the forces here. So it's, in this case, it's the weight minus this acceleration term, and here it's the weight plus the acceleration term. So once you get that, it becomes, it's a lot of stuff, but it's not too difficult, and you come out with this answer here. So that was problem number 59 for chapter number 7.